Hey folks, Dr. Mike Hotel here for RP Plus, RPU, Renaissance Periodization, and the world, really. I'm here on behalf of the whole world. So attention aliens watching this. This is Hypertrophy, Advanced Hypertrophy Concept Lecture number 5, Hypertrophy Stimuli. So what are we talking about today? We're going to talk about the exact hypertrophy stimuli, like what is it that actually at a mechanical, at a chemical, at a causative level, leads to muscle growth, makes muscle growth happen. Not just like training, but what is training doing to the muscle that causes growth to occur? All right, so a pretty deep question. The first thing we're going to talk about is what is the concern? Why do we want to know this question so precisely? Then we're going to talk about what the candidates are for these mechanisms. There are going to be 3, tension, metabolites, and cell swelling. Then we're going to finish off by talking about the implications for training and programming recommendations. So, what is the concern over wanting to know exactly what the hypertrophic stimuli are? Right? First thing, we already know hard training works. Okay, as a matter of fact, we know even better than that. We know that sets of 5 reps to 30 reps close to failure provide roughly equivalent growth over the medium term. So who cares how that happens? We have a template to follow. Why not follow it? Well, we can have really good training just not knowing a whole lot about what happens at a mechanistic level, but we can probably have better training if we do figure out what's going on. One of 2 ways. One, our training get better in the positive direction. That is, we can have training that is better than it is today because we find out exactly how to stimulate muscle growth. And another way is that training can get better by essentially curtailing or sort of chopping off the kind of training that's probably not the best idea because it's found out that that doesn't really stimulate a whole lot of direct growth mechanisms, right? So only if we know those direct growth mechanisms can we pair off training like that to make it not only to make it more powerful in a direction that works, but to take the chaff off, so to speak, and then have a more sleek training design where you can have a program that says, okay, this is my program, and every single part of my program grows muscle. And then no one can say, what about this thing you're doing? You're like, I don't know, maybe that, I don't know what it does. If you really know why training is caused and why muscle growth is caused and how you can have a perfectly efficient or very close training program, which is awesome, right? So, for example, if we really, really know how training works, if peak tension happens to be very unimportant, okay, peak tension is the most force developed by the whole muscle at any point during lifting. It's the highest peak tension you can possibly generate is your 1 repetition max. Just boom, just as much as you can push at one moment of time. It could be just for a second or 2, right? Some people think that peak tension is important for hypertrophy. Some people think it's not. We're not really so sure. So if it turns out that peak tension is just really unimportant, that as long as you have some minimum tension, maybe like a 30% of your 1 rep max, something you do like 30 or 40 reps, if that causes relatively equivalent growth to something that is a ton of peak tension, question is, why would you do sets of 10 or less, right? A lot of people, myself included, do sets of 5 to 10 reps because we think there may be something uniquely beneficial about a higher degree of peak tension, maybe for some muscle fibers and some muscle groups and so on and so forth. But gee, we have to admit that sets of 5 to 10 are uniquely probabilistic in their injurious nature. They more likely to get you hurt. Okay. You don't step under your, a weight you're going to do for 3 sets of 6 and think, I'll be fine. You're like, good God, I sure hope I don't break in half, especially if it's squats, deadlifts, bench presses, overhead presses. That stuff can get you hurt, man. What about sets of like 12? What about sets of 24? If you get hurt doing a set of 24, you basically just had it coming, right? There's nothing you can do in a set of 24 except for wild technique alterations and just insanity that's going to get you hurt. It's just such a low force. Right? Who gets hurt walking up and down hill? Nobody, right? You got to slip for that to happen. Higher forces have to happen. So if it turns out the peak tension is not very important, and we find this out through this kind of exploration of what exactly grows muscle, then, maybe we'll just never really do anything less than 10 reps. And that would be great. And then we see somebody at the gym that's trying to get jacked and we say, hey, why are you doing those sets of 6? And they say, hey, it grows muscle. And we can say like, no, it doesn't, idiot, and you're over here just trying to get hurt. Right? We already know like sets of like 2 or 3 don't uniquely grow any muscle. And most people in bodybuilding and hypertrophy circles, they don't train like that anymore. Used to be people did and say, well, you got to get strong and get big, but we already know that's probably not true. So maybe we can push it even further and say, anything less than 15 or anything less than 20 reps is a stupid idea. And there might be something to that. Now, we don't know that yet, which is why we're sort of investigating. Another one, if metabolites are more important than we think, then maybe chasing them is a really good idea. If it turns out that, all the way, like, training close to failure, training super heavy, all that stuff that grows muscle, if it turns out that it's just generating metabolites inside the cell, and maybe some of them that leak outside the muscle cell to other cells, if that's what actually causes muscle growth for the most part, which is actually a possibility, then chasing them is a real good idea. Then sessions that give you the burn are probably real up there on the list of things you should be doing to grow. And if you're not getting a burn consistently in training, somebody could say like, oh, look, you're missing out on at least a very big part of the picture, right? So maybe that's the case. And let's say that the pump, the muscle pump is one of our candidates here, cell swelling. Let's say it actually causes like a pretty decent amount of growth. Well, then tracking it and training to it is probably a good idea. So you can do a workout and you hit like not so great a pump. You can say to yourself, I need to change this workout somehow, probably doing more stuff or different rep range in order to get a good pump next time. Once you have good pumps, you're well on your way. On the other hand, if this is not the case, then it's really stupid to go after pumps when they might have just nothing to do with growth whatsoever. Right? It turns out maybe the pump is just a total just red herring, and someone's like, hey, I got a good pump. And you're like, okay, so? And they're like, well, it grows muscle. Like, no, it doesn't. And you're like, oh, shit. Maybe it doesn't even correlate with muscle growth. So knowing these exact concepts is a really, really good idea because, listen, we can already do good training, right? So you don't need to subscribe to RP Plus if you want to do good training. If you want to do your best training, we got to think a little harder about these things, get down really deep to the mechanisms. And in this lecture, we're going to get down to the mechanisms we at least know something about for the time being to see how muscle growth might actually occur. That's where we get to our training growth candidates. As of this presentation, which is in October 2019, we have 3 really good candidates for muscle growth, a bunch of other really small ones that we're not really sure about, but for now, 3 real good candidates in the research and in theoretical development that also intersect very well with what people actually do in the gym. There's always some quirky candidates in research and things people do in the gym that don't make any damn sense in between each other, but these are sort of real 3 heavy hitters: tension, metabolites generation, and cell swelling. So we'll go through all 3 of them in a bit, really in depth, one of the most deep dives on this you'll hear probably on the internet, and try to figure some stuff out. Of course, they may very well be other causes of growth. Damage comes to mind as potentially a cause, maybe not. Stress of some sort. A lot of times that's signaled through metabolites, but maybe it's not in all cases. But these ones have the most evidence for them, and they also explain most of the variance. In other words, if we already have at RP a sort of an integrated theory of hypertrophy that includes tension, metabolites, and cell swelling, and it seems to be that that theory currently, maybe just by sheer accident, seems to explain most of the variance in hypertrophy training. If there's not someone out there getting big without applying tension, metabolites, or cell swelling, probably applying several of them at the same time. So it seems that they're good enough to explain most of the variance, which does not necessarily mean that they're completely inclusive, but at least a very, very good start. And of course, we're always on the lookout for new research, new theoretical developments, new observations by athletes that maybe add one little situation here, maybe add a major variable, maybe subtract one. Maybe one of these is superfluous. So tension. What do we know about tension? Well, a really, really cool insight into tension and why it's one of the top contenders for hypertrophy causation is that it's been shown that muscle cells, individual muscle cells, have force transduction detectors, which are called mechanoreceptors, in various parts of that cell. A lot of them are located seemingly in the membrane at the sort of outside edges of the cell, and they literally just detect muscle force, or they detect force transduced along the membrane. So if you pull on a cell, well, the cell contracts somehow and generates force along the membrane, then, or along its various parts, then that force is detected. Okay, so force is occurring, and a muscle growth is signaled. Okay, sweet. So really tough to rule out tension as a candidate when there's literally a mechanistic thing that occurs. The body's actually detecting tension and almost certainly fueling hypertrophy with it. Now, how does this all work? Well, a lot of these mechanoreceptors are sensitive mostly to the cell that they're on. So the muscle cell, if it contracts, the mechanoreceptors sort of light up and signal other parts of the cell to start the growth process, potentially, right? But some of them are probably sensitive to whole muscle forces as well. So if the whole muscle contracts, but parts of it are not contracted, those parts that aren't contracted because tension is developed through the whole muscle, they'll get sort of some residual tension detection and they'll still turn on to some extent, right? First thing is a lot of muscle cells, probably almost all of them, don't run the entire whole length of the muscle, right? They connect at some point in the muscle and connect at another point in the muscle. And there's a whole bunch of muscle outside either way, both, side to side and front to back. So when you pull on their distal ends, when a muscle contraction occurs and there's pulling on every structure in the cell, then some of that pulling might actually generate growth triggering tension as if the cell itself was contracting, right? Especially stretch has been shown to be hypertrophic, tension developed under stress or under stretch. And if those muscle cells are being stretched a lot, that is actually tension that is probably detected by the mechanoreceptors, and cell doesn't have to be on for that sort of thing to happen. So there is some of that. And connections between cells are sometimes pretty, how do I say this best? A lot of times the connection between cells is pretty tight. So, or rather shear resistant. So when one cell is pulled, another cell a lot of times just, for the most part, goes with it, right? So when a lot of cells around a cell are contracting, even if that cell's not contracting, a lot of times the motion and the tension through it is mimicking almost exactly like it would be contracting anyway, okay? That being said, this is not a perfect system where a bunch of cells can just pull another one along. A lot of contraction is cell-specific, and this has been shown in a number of studies. And most adjacent cell contraction, if cells are contracting next to a muscle cell, probably doesn't lead to much tension generated, or as much as you'd want in a non-contracting neighbor cell. So to all that complexity is to put the following, that yes, you can get some growth just by contracting other cells around a cell, so that the cell itself doesn't necessarily have to be growing. But a lot of growth, probably most muscle growth, is caused by the cell itself contracting, not just adjacent contractions around it, right? Another interesting take is, this has been shown at least a couple times, concentric muscle contraction triggers muscle growth of a certain kind or a certain manner. Eccentric contraction triggers another kind of growth, and isometric contraction triggers another kind of growth, or rather I say it triggers different growth pathways, right? So there might be something to this, and we'll say this formally in just a bit, that training with eccentric loading, concentric loading, and some isometric inclusion might be the best way to get all the growth that you possibly can, and training just one or just two of them might not be enough. Now, here's a really, really, really interesting point. Passive tension grows much less muscle than active tension. So if you take a muscle cell and you pull it apart, okay, it's got a bunch of essentially stretchy elements to it, elastic elements that generate a ton of tension right back, right? So if it's like a rubber band, you pull on a rubber band and there's a whole lot of tension occurs, that actually generates some growth. Stretch is an independent hypertrophy mechanism. However, it generates way less growth than if you have that sort of stretch, but you also activate the muscle cell and it actively tries to contract against that stretch. So it turns out that force transduction is probably not everything, but the actual contraction internally seems to be something that helps. So how does this happen? Maybe it's not just the tension itself, but some combination of tension and metabolites of intracellular contraction. And we'll get to those metabolites in the metabolite section, but there's a lot of work done in molecular level to show that what probably happens is force is detected by the mechanoreceptors, and they start to activate some downstream growth processes. And some of these growth processes, or rather a molecular chain of events, involves metabolites like phosphatidic acid, calcium, for example. And phosphatidic acid and calcium are really essentially just occur in really high amounts in the cell pretty much during muscle contraction, or it's just sequestered away when muscle contraction is not occurring. That is, when the cell itself is active, when actin-to-myosin cross-bridges in the cell are generating tension. So it might be, and we're not so sure, that if you just pull on a cell or really deform it, you can generate a lot of force through the cell, and the mechanoreceptors will detect that. But when they detect it and there's not a lot of presence of internal metabolites to signal that the cell itself is generating that force, there might not be a whole lot of hypertrophy that's caused. But if you have the internal metabolite generation, there might be a lot of hypertrophy that's caused in addition to the tension that's being perceived. So if we take that all together, we have a couple of take-homes on tension. First, whole muscle tension is somewhat anabolic to all/most cells, which means that if you do, a stiff-legged deadlift for sets of 8 or something like that, and your whole hamstring is stretching and contracting, there's a chance that some of the cells or faster motor units or something like that, or muscle cells that are positioned to mostly be active in leg curling instead of the hamstring movement you see in hip hinging, there may be a chance that those cells are not very active or not active at all, but it turns out that they probably still grow to some extent just because the whole muscle is generating a crap load of force through it. So there's something to be said for that. So at the very least, we don't have to super overthink training to get really good results, but maybe we do to have to get our best results. The second point is that per fiber, and thus per motor unit, because all motor units activate all fibers in them equally, per fiber tension is likely much more anabolic than passive tension derived through stretch or through other cells contracting around the muscle cell and pulling it along for the ride. So when you want maximum muscle growth, you'd probably want to at some point involve the activation and internal tension generation, which is mostly the same thing, all of the cells that you're targeting because you want all muscle cells to grow, right? Now, tension via stretch is mildly anabolic. If you just stretch a muscle, it grows, but tension via internal contraction is very anabolic. So muscle cells grow a lot when they themselves contract and generate forces within them rather than the forces coming from stretching or deformation from the outside. Probably the best kind of hypertrophy is when both are occurring, which is why tension under stretch, both at the same time, is super, super hypertrophic and is actually uniquely hypertrophic, right? So if we take all of this together, we have kind of a recommendation for how to train to maximize tension. We want to generate lots of active tension, which is to say we don't just want to do stretches, we want to do actual contraction. We want to generate it concentrically, isometrically, and eccentrically at various points in our training. We'll talk about later how to get that. That's pretty straightforward. We want to introduce stretch under the tension. So you don't just want to do like just isometric contractions over biceps like this. You probably want to generate a lot of tension at a lengthened position of all the muscles at some point in training. And you probably want to activate as high of a percentage of muscle cells to actually themselves contract as possible for max growth stimulus, because as we saw earlier, a lot of the cells around can be contracting, and it turns out that muscle cells themselves that aren't activated might, receive some hypertrophic stimulus, but maybe not nearly as much as we would want for best results. All right, that's tension. Certainly candidate number one for hypertrophy, probably causes most of the hypertrophy. Now, metabolites. Okay, we have, from the last section on tension, we have this quote, "So perhaps it's not just down to tension itself, but some combination of tension and metabolites of intracellular contraction," which is like actin and myosin-based contraction. So what we're saying is this: tension might actually cause most of its muscle growth, not through the fact that the tension is being detected, because if that was the case, stretch would cause a lot of hypertrophy. It doesn't. It just causes a little bit. What might actually happen is that when we generate tension internally, part of that process, a side effect of it, or the process that causes it, is the generation of a high degree of internal metabolites. For example, phosphatidic acid has a lot of evidence as a literal cause of muscle growth, and it's a huge part generated in the internal tension-producing process in a muscle cell, right? So is it the tension that's causing the growth, or is it the phosphatidic acid that's a huge part of that process to generate tension? What about calcium? Calcium is a huge candidate because calcium has to essentially flood out of the sarcoplasmic reticulum into the muscle cell itself to get actin and myosin to talk to each other. And calcium seems like a real high candidate for, if you have a big calcium flood, you're almost certainly generating highest tensions. And calcium flooding is super related to how close to failure a muscle cell gets and how high of tension it generates. As both are super indicative of how much calcium, super correlated how much calcium appears inside the cell. So it might be that hypertrophy occurs in part as phosphatidic acid detection and in part as calcium detection, right? And again, how do we say, well, it's not just the tension itself? It could be the tension itself, but when you stretch a muscle cell and actually generate a crap load of tension through it, if it's not activated, it doesn't grow a ton of muscle, not nearly as much as we would expect. Something's missing. Internal metabolites may be that very thing. Notice we said internal metabolites. one of which might be lactic acid. Some evidence there, and almost certainly other metabolites, various ions are probably involved in that process, right? So when these metabolites are generated inside the muscle cell itself, when it's contracting, it's making them, they almost certainly play a big role in growth stimulus, right? And this is, of course, to repeat myself fifth time, this is evidenced by less growth via passive tension than active tension. Okay, active tension causes much more growth than passive tension. It could be that there is a way that active tension actually pulls on certain structures that really causes the growth, but another very high likelihood is that the pull from passive and active tension is really kind of similar as far as the cell is concerned, but passive tension doesn't generate any internal metabolites, and those may be the ones that cause the most growth, right? However, the big question here, when people say metabolites, they say like the burn, metabolites writ large, not just internal to the cell. Now, hilariously enough, metabolites internal to the cell cannot be detected by your nerves nociceptively, right? There's no pain to detect because the nerves are external to the muscle. So if you only generate a high degree of calcium inside the muscle, which is probably something that happens with like sets of 5 or something like that, which cause a lot of growth, by the way, almost none of that calcium leaks out, or none of that, for example, lactic acid leaks out because it just stays internal to the cell. It causes a crap load of hypertrophy there, very likely, but doesn't leak out and cause the nerves any pain. So sets of 5 probably don't give you a burn. So when we say metabolites, we're actually talking about something else. So here are the big questions. Can metabolites, first of all, leave the cell in which they were generated? The answer is definitely yes, but we're not sure on how big of concentrations they leave the cell and go to other cells versus how much concentration is required to grow muscle in the cell itself. Because it could be like, it'd be 100 units of lactic acid inside the cell itself, or 100 units of calcium, and then if the adjacent cell is not contracting, right, and those leak in, how much of them really leak in realistically before you hit failure and stop and have to wash out the metabolites? Well, if it's like 5 or 10 units of both of them, maybe the requirement for hypertrophy for trained athletes is like at least 30 units of lactic acid and calcium. Well, then like, metabolites just are real cell specific at that point. There's just not enough of them leaking across cell lines. And then you have to actually activate every single cell that you want to grow, which is very, very possible, right? So question 1, do they leave the cell in which they were generated? Or and question 2 is, do they enter adjacent non-contracting cells, which is also probably very true, right? And then number 3 is in amounts high enough to cause growth in those cells. At least one study in lactic acid says yes. But one study, that's really not that great. And, lactic acid can leave. Does calcium leave to a large extent? Probably not a ton. Does phosphatidic acid? I'm not sure. So we're left with this idea that metabolites are probably very important. Because remember, metabolites are really just molecular products generated by muscle contraction in some way, shape, or form. Almost certainly, even you could say tension, if the molecules that detect tension generate other molecules that then message to the cell nucleus to grow muscle, those are technically metabolites. So at almost some point, just by definitions, metabolites cause probably 100% of hypertrophy. But the real question is, metabolites generated in one cell, do they leave and cause other cells next to them that maybe aren't contracting? Do they cause growth? And how do we know which ones leave? Well, they're the ones that hurt our nerves. So when you're doing like a set of 4 or something like that, are you generating metabolites inside the cells that are actually contracting? Of course. But are you getting metabolites to leak to other cells? Probably not, because your nerves would detect them and that would be registered as pain. When you're doing a set of 25 close to failure, there is lots of metabolite leakage that occurs to a whole bunch of cells, probably gets into other muscle cells. The question is it in high enough concentrations to cause any muscle growth? And we're not so sure about that. The lactic acid studies say yes, but we need much more data to say how much it is or to what extent that actually happens, right? So last slide here on metabolites. Do metabolites cause growth inside the cell which they are made? Almost certainly, and perhaps most of it. At some level, metabolites probably cause all growth because just one molecule that even the tension receptors signal upregulation in is technically a metabolite, right? Do metabolites cause growth inside cells adjacent to where they are made? Maybe, but probably not a ton of it, right? And that's basically, you can get fiber-specific hypertrophy if you stop real short of failure all the time. Your faster twitch motor units probably won't grow a lot. And you can actually get some pretty decent lactate accumulation and metabolite accumulation, but probably only so much of it crosses cell boundaries, and you probably need a whole lot of it to trigger a lot of hypertrophy, right? The amount of lactic acid that occurs in the cell in which it's being produced versus in the adjacent cell, I mean, if half of it crosses, then you just have half, right? And that might not even be enough to trigger any growth, or maybe just in beginners or something like that. To make this a little bit more complex, we can say, okay, what if metabolite growth really did affect adjacent cells? How would that work? Well, you start doing a set, and your slow twitch fibers are the ones that turn on first. Let's say it's a set of 20. Your slower twitch fibers turn on first. Your faster twitch fibers are not active very much, to some small extent. And the thing about slower twitch fibers is that they just don't leak a lot of metabolites. They're really good at processing them and sequestering them and buffering them and reusing them, like lactic acid. They just reuse internally. It just goes right into glycolysis, goes right into oxidative phosphorylation. So we could say, okay, we're going to use the slow twitch fibers to make a bunch of metabolites. Those metabolites are going to cross over and and cause growth in the faster twitch fibers. So we never really need to go super close to failure or go heavy, because we can just get that translocation of metabolites. Well, problem is the slower fibers don't leak a lot of metabolites. So there goes that, right? So until you start activating faster twitch fibers, the metabolite leakage is not a really big deal. And the good news is that the later activating faster twitch fibers, they do leak a ton of metabolites, very likely, but at that point, they're already contracting. So what is it that we're trying to contract further, or what is it that we're trying to grow muscle with further? For example, let's say we have the 3 biggest fibers in our biceps or something like that, and the least big of the fibers starts to really leak some lactic acid, and it leaks into the other fibers and start to cause them to grow. Well, in about a rep or two, they're going to start to turn on anyway. So this idea that, okay, we can really just use some of our muscle fibers to grow the others, even though they don't contract, by the time the muscle fibers that produce the most lactic acid, the faster twitch ones, are actually active and producing a ton of metabolites, then all of the other muscle fibers that we're trying to sort of activate without them having to contract, they started contracting anyway, or are going to be very shortly. So there's kind of nothing extra to grow at that point. The one trick here is that vascular occlusion, right, that kind of training, occlusion training, Katsu training, might alter this a bit, because it might start to sum metabolites really quickly and allow the metabolites to sum up way before the faster twitch motor units are really starting to turn on, which might grow a bunch of muscle that isn't yet super active in its tension generating abilities. So we may get more of that growth spread from one cell to the others via this technique. But that's a really, really big maybe, because fatigue also hits way faster in those sets. So you would think, okay, the metabolites are really flooding, we're going to get tons of growth now, and then you reach failure, right? So it might not be the case, but in any way, certainly something to be interested in and look further. All right, last growth mechanism is cell swelling. Really good thing about cell swelling is it gets short shrift a lot in a lot of writing on hypertrophy, but it's one of the ones that has some really good studies behind direct mechanistic demonstrations that it causes hypertrophy. Okay, so cell swelling almost certainly just literally causes muscle growth, right? To the point where they can inject stuff into a cell to make it blow up a bit, and it actually hypertrophy mechanisms start going. There are some doubts, however. Is this the myofibrillar hypertrophy, the actual construction of actin and myosin that we are looking for, or is the construction of essentially titin, nebulin, and a bunch of other framework proteins that make the cell bigger, but not any more strong and not in any way that lasts very long? So as soon as you stop getting repeated cell swelling, the cell just shrinks back to its normal size because it doesn't need to be that big anymore. Maybe, we're not so sure, which is why cell swelling doesn't get a huge high ranking for us as a growth mediator, because it might not explain a whole lot of the variance. Another problem with cell swelling is that sets of 5, sets of 6, sets of 7, sets of 8, they are reliably grow muscle as well as any other set, but they cause almost no cell swelling whatsoever, or very little of it. So maybe cell swelling is not this huge deal, right? And that gets to the point of how potent of a mechanism is it? Probably not very potent, but it probably contributes to some extent, right? So we can tentatively suggest that the pump probably causes some degree of growth. We're going to talk about later why the pump might cause some growth outside of its relationship to cell swelling, that precisely the kind of metabolite accumulation and super high tensions in all the fibers that cause cell swelling, that cause growth in their own regard, might also cause the pump as a secondary feature. So the pump might actually be a real good detector for hypertrophy in many cases, even though the pump itself might only be responsible for a small fraction of the growth. All right. Hugely important. We're going to take all this together. What does it imply for the training process? Okay. So first implication is muscle cells really only develop a high concentration of internal metabolites, the ones that cause probably most muscle growth, when contracting at high percentages of maximum ability, right? So if you get a muscle fiber to contract at 25% of its maximum voluntary contraction ability, you produce all these metabolites, and they usually just get basically recycled as quickly as they're produced. You can sustain a contraction like that for a really long time and cause almost no muscle growth whatsoever. This is evidenced by the fact that marathon runners, they contract a bunch of their lower body musculature and almost never maximal. And they, are doing this for hours on end, and they're not hypertrophied to any extent, possibly even atrophied to some extent. And this is not all nutritional and so on and so forth. There's definitely a force-mediated or an accumulation of metabolites-mediated effect there. So because maximum contraction or threshold contraction is a good idea for every single cell, then approaching failure is probably a good idea on the per fiber level, right? So if you're going to grow a muscle fiber, it had better be working real hard, working so hard that it generates a lot of internal tension for some time, and that it also generates a lot of internal metabolites, very, very high concentrations, which are probably what signal the cell to hypertrophy, right? Point number 2, tension in the highest threshold motor units is only maximized when they themselves contract. Yes, there are some ways to get tension going with just peripheral activation, but nothing beats the contraction of the motor unit itself, right? And not only does the tension have to be applied, because we can do that with stretching to some hypertrophic benefit, but not much, there has to be probably a lot of internal metabolite generation during that can only be caused by that muscle contraction, right? And that probably has to occur with a contraction for a length of time. So for example, tension is an interesting candidate for hypertrophy, but you might get this idea that, okay, so we take, let's say, a barbell that's loaded with 85% of a run rep max, and we do a single rep with it, okay? We put it down. That single rep generated with as fast as movement as possible almost certainly activates the vast majority of your muscle fibers, and probably at the highest forces that they're capable of exerting, right? And we can even say, okay, fuck it, 85 is not good enough, 92%. I mean, it's been shown a bunch that anything from 90 to 100 is roughly equivalent in how much per fiber force is being generated. And a lot of it, whether or not you make the lift, comes down to technique and which way you're pointed. So, and the resultant velocity too. The force-velocity relationship is very valuable, but within very close velocities, the forces are sometimes roughly equivalent. So what ends up happening is you do a rep like that of 90%, then you stop. You rest for a while. Then you do another rep of 90%, you stop, you rest for a while. People train like this. Powerlifters train like this. And it's not very causative of hypertrophy. It certainly causes some, but not nearly as much as you would expect. I mean, a powerlifter can do, a whole bunch of what are called, effective reps, maximally effective reps at this point, and not get a lot of hypertrophy. Sets of 2 is not a way to grow a lot of muscle, even though every single one of those 2 reps is as hypertrophic as it gets because it produces a maximum amount of tension, you would think, right? However, what is missing from that is that those muscle fibers that are the highest threshold, they're not, and actually all muscle fibers in a set of 2 or set of 1 rep, they don't produce tension for long enough at high enough levels to, the levels are as high as they get. The length is the problem. They don't produce tension for long enough to really start to summate internally to themselves, not leak out, a whole lot of metabolites that probably cause muscle growth. Like you get an increase in calcium concentration in a cell when it does a set of 1, right? But then it goes back down and you rest for a long time and then a set of 1 and it goes back down. So you might get some hypertrophy there. But if you get a cell close to failure, it generates a ton of calcium or a ton of phosphatidic acid, boom. And then for several seconds, you keep contracting and the levels are super high, super high, super high, and then you reach failure and they fall off, right? That might be like 5 or 6 times as much exposure to those metabolites internally to the cell than just singles or doubles would. So this is why I think maybe the sets of 5 and above tend to cause more hypertrophy than sets of 5 and below is because of that exposure, right? But let's be clear, most of that exposure is internal to the cell. So you can't just generate a lot of metabolites in the muscle as a whole and expect all those metabolites to leak in and really, really activate a bunch of growth. It probably happens to some extent, but a small one. So point number 2 is we want tension to be very high in every motor unit that we're trying to train, and we want it to be high for quite some time, which means probably at least 5 repetitions worth of time under tension, so to speak. Okay, so we've got that. Point number 3, most fibers contract with either heavy loading or near failure conditions, which is, by the way, to say the same thing. Okay, faster motor units don't contract unless they're required to generate the force necessary to keep the movement going. If the weight is really heavy, they're required to generate enough force to keep the movement going. Or if everything else is tired and you're in really high reps, as you reach failure, in order to keep doing reps, you have to activate those larger, faster twitch muscle fibers, which grow most of your muscle anyway, to keep doing more reps. So point number 3 is basically saying not only does the individual muscle fiber need to be challenged for a long time, the muscle as a whole probably needs to either be trained heavy or go close to failure. This is a super, super interesting implication of training that has really, really far-reaching effects. And we know it already from experimental direct evidence, or we have a feeling about it, but it matches the physiology seemingly so well that it's a very, very powerful realization. In other words, if someone says, hey, we're going to train to get jacked, the next question you have to ask if it's proper training is it going to hurt a lot because there's lots of metabolites? Am I going to be grinding a ton of close to failure sets, or is the weight going to be crushing me? If it's none of those 3 things, or even those 2 things of going close to failure or training really heavy, you're probably not in for a lot of muscle growth, which is another way of saying training's going to be hard, right? Can you imagine a way of hypertrophy training that was neither heavy nor got you close to failure? That would be awesome. I would train like that immediately. But unfortunately, it's probably not likely because of the very fact that muscles only really grow when you really, really challenge them. When they're generating lots of tension internally, when the metabolites internally are really, really high. And in order to do that, you got to push muscles either really, really heavy or closer to failure, which is actually the same identical thing. Because if you're lifting at 5 RM and you lifted 4 times, that's a 1 rep shy of failure. Same idea, right? Now, this is an interesting idea. It may or may not be true. It's worth considering. Slower twitch fibers or intermediate twitch fibers might need longer times to contract and sum up enough tension and internal metabolites to signal the most growth. Because remember, those fibers churn through metabolites really, really well. They're really high endurance. So to really sum up very high metabolite levels inside them, they might actually need to contract for longer than the faster twitch fibers themselves. So higher rep sets may at times be necessary for full development. Like if you just do your fastest possible, if you just do low rep sets of 5 to 10, you may be missing out on intermediate fiber growth, which has been shown to cause some good degree of muscle growth, right? Now, we have an understanding from direct experiments that heavy training and lighter training are roughly equivalent for hypertrophy. How? If lighter training activates the faster twitch motor units and the slower ones for growth, and the heavier training only activates really and only grows, it activates all of them, but it really only allows internal metabolite summation to occur with these faster units and maybe leaves the slower ones behind. Well, here's the deal. By the time, and this is point number 5, by the time that you get towards the last reps in a very high rep set, you have 2 problems. One, you have nervous system fatigue. So when it comes time to do a 25 rep set to failure, when it comes time to do reps 21, 22, 23, 24, and 25, you are so tired mentally, neurologically from doing the first 20 reps that you might not get full activation of your nervous system of those high threshold motor units that you're now trying to activate when you're really tired. So you might miss out on a good deal of faster muscle twitch activation, which if you were just doing a set of 5, it would be from the first rep, you're activating maximum all the faster twitch motor units. Second rep, all of them. Third rep, fourth rep, fifth rep, all of them, right? Yeah, the slower twitch guys don't get as much love and don't get as much stimulus, but the faster twitch ones grow so much more anyway. In super high rep training, it might be the opposite that's occurring, right? And in addition to that, even if the nervous system is just up to par, you're like super psyched and It just so happens your nervous system doesn't get tired. You can actually get local limitations of contraction by excitation-contraction uncoupling, which means, for example, if you have a ton of metabolites in the neuromuscular junction, so we have the nerve, we have the muscle itself, and we have sort of a little junction between the two, and that's where neurotransmitters leave the nerve and tell the muscle to contract, right? If you have a ton of metabolites in this space, which definitely happens with super high rep sets, you might actually have a problem, not just this space, but around the nerve, in the periphery of the muscle. What ends up happening is you have a problem with excitation-contraction coupling, which is to say that the nerve could be saying fire, 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 but it has trouble releasing metabolites, or trouble releasing neurotransmitters. There may be trouble accepting neurotransmitters. There may be trouble at any part of the distal part of the nerve and the proximal part of the muscle itself. There may be problems in various mechanisms by which excitation of the nerve transduces and actually causes muscle contraction. You can actually feel this effect, sort of, when you're really close to failure on a set of biceps, for example, in a mega drop set. Right. So in a mega drop set, you do like set of 5 to failure, then a set of 5 to failure, and like less weight, 5 to failure. After a while, you get this idea that you're pulling as hard as you can. You might even be like, you have metal in your headphones, you're good to go. Nervous system, you're just trying as hard as possible. You don't feel neurologically fatigued, which is pretty easy to feel. It's when you're just like, oh, get me out of here. I just don't want to try anymore. You're trying as hard as you can, but there seems to be this inability to actually get your muscle to contract. There's almost like a loss of mind-muscle connection to where like, I'm trying, I just don't feel like anything's happening. That's a real thing, right? And the feelings might be illusory. It might be all mental. But this does happen when metabolites are super high. So we got to be careful about assuming that sets of 25 and 30 are the best possible way to grow muscle, because by the time you get to number 20, you might be neurologically super fatigued and you might have trouble activating those faster twitch motor units as much as they could possibly be activated. Now, of course, they're probably active to some extent the entire time, but they're probably not maximally activated until the very end, and that's where most growth occurs. So what end up happening is sets of 5, very heavy, you get a ton of faster twitch activation because it's all fresh and new and really good, which is good. It gives you maybe 90% of your potential growth. And then for sets of 20 to 30, you might get a bunch of it, all the slow twitch activation you need, or hypertrophy stimulus, all the intermediate twitch, most of the faster twitch, but not all of it because of these problems with the neural fatigue and with excitation-contraction coupling. And then you might get only up to 90% of maximum hypertrophy. So what's the answer to that? Well, maybe you do some of both. Maybe sets of 10 to 20 are on average, maybe they get you 95% of hypertrophy because they combine both in some extent. Or maybe they net 90 as well because there's some fatigue in them, but there's also a lot of, less fatigue than there would be in the 25. There's some good slower twitch intermediate fiber summation of metabolites and activation, but maybe not as much as in the 20 25. So it might be that sets of 5 to 10, sets of 10 to 20, sets of 20 to 30 each activate only about 90% of potential hypertrophy. So how can you do your best? There's at least a couple of studies that show that combining repetition ranges probably works to maximize results, but these have to be very, very precise studies. When you have 90% as much hypertrophy between two rep ranges, it's almost undetectable unless you have like 100 subjects or something like that. But theoretically, it makes some sense. It might be worth considering doing that, right? So point number 6 just reflects what we just said. Near failure training with heavy loads probably grows the higher threshold motor units the best. Near failure training at lighter loads always causes pumps and lots of metabolite leakage, which addresses those growth pathways. So it probably has its own place in training. So we can take all of these likelihoods together and go into programming recommendations. So all this together, we're going to weave it back into programming recommendations. First thing we're going to see is we already knew a lot of the stuff, but some of the stuff we know better and we know more certainly because we understand the physiology. Point number 1 in programming recommendations. Any less than 5 reps in reserve of training is probably a poor use of training time, as near failure training is just more hypertrophic for all of the reasons we talked about, right? It activates the most fast twitch motor units. It allows the internal metabolites to sum up to really, really high levels, which probably causes a lot of hypertrophy. Number 2, already mentioned this, there may be unique benefits to training in the low repetition ranges, in the high rep ranges, and the moderate rep range may offer the best trade-offs or just be roughly average of the two. Probably your best bet is to some extent use all 3 ranges by a very small margin, which is to say any range alone can cause near optimal gains, right? It's probably like if you just train with sets of 5 to 10, you get 90% of the growth you are supposed to get. If you just do sets of 10 to 20, you get 90% of the growth you ever get. If you just train sets of 20 to 30, you get 90% of the growth you want to get, and so on and so forth, right? An interesting concern there, however, is the following. Faster twitch motor units probably don't require as much physical work, right? As many reps with maximum tension, so on and so forth, as many sets, as do the faster twitch, as do the slower twitch muscles. Slower twitch muscles may also recover faster. So when you're designing a training program over the course of the week, it's probably unlikely that 75% of it will be in the 5 to 10 rep range and only 25% in the lighter rep ranges. It probably skewed the other way, where maybe only 25% of your training needs to be in the 5 to 10 rep range. It's a little bit injurious, a little risky, but it checks the box for those faster twitch motor units. And then maybe a full 75% of your training can be between the 10 and 30 rep range. That way you get all the benefits of that range, and it's safer on average to do, and you can recover from it relatively faster, especially from a neurological perspective. Point number 3, on the metabolite front, if your training is not causing any notable burn, it might not be optimal, because metabolites probably cause some degree of hypertrophy. And if your training is causing amazing pumps, it's very likely to be anabolic, both directly via cell swelling and indirectly because you're probably training really close to failure, which is good for hypertrophy, and generating a lot of metabolites, which is really good, which also causes lots of pumps. And producing lots of forces actually causes the muscle to contract and essentially act as its own sort of vasoconstrictor. And when you release, you get reactive hyperemia, which causes a pump. So basically, if you're not getting pumps, it should be in the 5 to 10 rep range at most, probably in the 5 to 7 rep range. Anything above 8 reps, if your training is not causing reliable pumps, you might not be training hard enough, close to failure enough, might not be eating enough carbohydrates, so on and so forth. So pumps, probably indicative of really good things coming your way. Lastly, point number 5, because concentric, isometric, and eccentric hypertrophy seem to trigger potentially different pathways for muscle growth, you probably want to do lots of all of these, which means what? Well, you want to do a concentric on almost every rep, which you're going to have to. You want to control the eccentric on every rep. I don't mean super, super slow. Just make sure you're still active on the eccentric. And some pauses at the bottom of a movement or at the top of a movement, doesn't have to be in all movements, are probably really good. Pause and squeeze at the same time is really good. Interestingly enough, bodybuilders, for a long time, bodybuilders do a lot of stupid shit that doesn't work just out of tradition. But some of the stuff they do, a lot of it is really, really effective. A lot of bodybuilders swear by peak contractions and top holds and stuff like that. And then there might be something to that because of the isometric contraction benefits. All right. So, summary implications of this whole thing. The direct causes of muscle growth via training are probably very complex. And they are also still a little bit mysterious. So we don't know everything here. This is a very speculative talk. Right? Please remember that. But we know that training is probably tension, metabolite, and cell swelling mediated at some level. We're not sure what percent of what accounts for it, especially the complexity that the way your body might detect tension might in large part be by the active tension generation and thus the metabolite generation internal to the cell, right? But there has been I don't know about debate, there's been some conversation about which one of these is really the one that causes muscle growth. From a training perspective, I think this debate is potentially fruitful, but not necessarily a good idea. Why? Because there's no reason to think that there is only one training-mediated cause of muscle growth. There is not one mediated cause of muscle growth for other factors. For example, let me ask you a question. What grows muscle? Is it insulin? Is it testosterone? Is it leucine? Actually, all three of those grow muscle. It's been demonstrated a whole bunch. They cause mTOR activity. It leads to muscle growth. So can someone say, well, it's really not testosterone, it's leucine, or no, it's really just leucine, it's not testosterone? That's the ridiculous debate. It's all three of those things, right? So what do you do to grow the most training? You eat an adequate amount of carbohydrates, so you're not very low on insulin. You make sure that your hormones are in balance. You don't overeat or undersleep so that your testosterone is super low. And you eat plenty of protein to get a good leucine spike with every single meal and grow muscle just like that. You have to check 3 boxes, and a whole lot more actually, in order to grow muscle from a sort of like nutraceutical perspective. So what about from a training perspective? Why is it that there is no debate about which one of the insulin, testosterone, or leucine grows muscle? They all contribute to muscle growth in their own ways. And of course, a bunch of other things like myostatin, for example. Why is it that we're looking for just one causative variable of hypertrophy from a training perspective? Is either tension or metabolites or cell swelling? Maybe it's all 3. Maybe there's even more of them that we don't know about, right? Until we know more, right, your best growth chances is to train close to failure, 4 reps in reserve and lower, and train everywhere in the ranges between 5 reps per set, 30 reps per set. And if you're avoiding the burn, if you're avoiding the pump, if you're avoiding deep stretches and peak contractions, you're probably doing yourself a disservice. So really good training is sets of 5 to 30 with lots of burn, lots of pump, lots of deep stretches under tension, peak contractions, and that's about it. Whew, that was a doozy. Folks, see you next time for number 6, which just happens to be on damage and growth. See you then.